So, as example of solution for linearized flow problems, we consider subsonic flow past wavy wall, and the solution gave us few important observations, and the most important of them that we found the perturbation is maximum on the wall itself, and as we move away from the wall the perturbation decreases. There was an attenuation factor. We also saw that the attenuation reduces as Mach number increases. Now, we will consider this same example in supersonic flow, that is a supersonic flow past a wave shaped wall. So, this is what we will be discussing today, a supersonic flow past wavy wall. The problem is essentially the same, that is we have an wave shaped wall the amplitude once again is h and length of one wave is once again L. That is, once again the wall is given by y minus h sin alpha x equal to 0, where alpha is 2 pi by L. The governing equation in this case is once again 1 minus m infinity square or since 1 minus m infinity square is negative, we write this as m infinity square minus 1 d 2 phi d x 2 minus d 2 phi d u y 2 equal to 0. As you have mentioned earlier that this equation is hyperbolic, and of course, we do not need to specify boundary condition in all boundary, which is the property of hyperbolic partial differential equation, and also they represent a propagation problem. Now, this time we can consider or write m infinity square minus 1 equal to beta square. Please note the change in the sign of beta square. In the subsonic case, we consider 1 minus m infinity square to be beta square, but now we take m infinity square minus 1 equal to beta square, and then this equation becomes d 2 phi d x square minus 1 by beta square d 2 phi d y square. Once again it must be remembered that phi in this equation is perturbation potential, that is phi is perturbation potential and its gradient gives only the perturbation velocity, not the total velocity. So, to find the total velocity, free stream velocity must be added to this perturbation velocity, which is gradient of phi. Now, this is our familiar wave equation. And we have very well known solution for this, which is phi x y is x minus beta y plus g into x plus beta y. The solution is quite well known. Now, for the time being we set g equal to 0. And we will see why g is chosen to be 0. In fact, it has something to do with the direction of the flow and which makes a distinction between upstream and downstream, which is again a property of the hyperbolic partial differential equation. Now, to find the explicit form of this function f, we consider the boundary condition. The boundary conditions are of course the same as in case of subsonic flow, there is no change in boundary conditions. Using the wall boundary condition, which says that the slope of the streamline is same as the slope of the body at which is of course linearized as before, which gives that d phi dy at y equal to 0. We see here that instead of evaluating the velocity component on the wall itself, we are evaluating at y equal to 0. That is the linearization or approximation, but consistent with the linearized perturbation theory, and this gives minus beta f prime x minus beta y at y equal to 0. Remember that f prime is that is f is differentiated with respect to its argument. Now, d phi dy at y equal to 0, which we have already seen, is minus u infinity h by beta sin alpha x equal to this is what we get substituting d phi dy y equal to 0, whereas before d phi dy So, this is the function explicit form of the function f, and hence our potential becomes, the perturbation potential is phi x y equal to function of x minus beta y, which is or in terms of Mach number, this can be written as sin alpha x minus root over m infinity square minus 1 into y. The perturbation velocity components are d phi dx, that makes u infinity alpha h by beta cos of alpha into x minus beta y. U infinity alpha h cos of alpha into x minus and the linearized pressure coefficient is minus 2 u by u infinity, that gives 2 alpha h by beta cos of alpha x minus beta y, or in terms of Mach number, which is root over m infinity square minus 1 cos alpha x minus root over m infinity square minus 1 y. So, this is the linearized pressure coefficient, and what we see here, that we did not need to satisfy any boundary condition at infinity to obtain this solution. That is again the special property of hyperbolic partial differential equation, that we do not need to satisfy the boundary condition at all boundaries. Now, looking to these perturbation velocity and pressure coefficients, what immediately we can see is that there is no exponential attenuation factor here. So, the first observation that we can make is no exponential attenuation factor in u v or C p, and it simply means that the perturbations do not vanishes as we increase our y, which is unlike subsonic case, where we saw that the perturbation decreases as y is increased. In this case, we see that of course, the highest perturbation is obviously still on the wall, but it is not decreasing with increasing distance, meaning that in a supersonic flow the perturbations will not vanish even at very far distance, very far off from the body. So, supersonic perturbations will not vanish even at very great distance from the body. In fact, what we can see here, that the perturbation remain constant, as long as this remain constant. So, now x minus beta y equal to constant is essentially a straight line in the x y plane. So, the perturbation is constant along the lines x minus beta y equal to constant. And obviously, these lines makes an angle beta, or we say that or we can say that the constant perturbation along lines with that are inclined at Mach angle to the undisturbed stream, that is along any line which makes Mach angle with respect to the undisturbed stream, the perturbation remain constant even up to infinity, or in practical case to a very large distance. Now, the lines which makes Mach angle with respect to the undisturbed stream are called, as before we have called them, the Mach lines. These are the Mach lines or the characteristic lines. So, the perturbations remain constant along the Mach lines or the characteristics lines. Now, once again we see that this has nothing to do with the boundary conditions, and in fact, this is the property of the basic solution itself. So, this is independent of the boundary conditions. This fact is independent of boundary conditions. Independent of boundary conditions, or rather that the flow is such that its perturbation remain constant along Mach lines irrespective of whatever body shape we are considering in a supersonic flow. So, this property is contained within the specific solution f equal to constant along x minus beta equal to beta y equal to constant. So, property of the solution itself, of the general solution f equal to constant along x minus beta y equal to constant. And similarly we can see g equal to constant along x plus beta y equal to a constant. Now, as you can see that with respect to any wall or any streamline Now, these set of characteristics are, as you can see, inclined downstream and meaning that they are originating from this wall and they carry the information from the wall to the field, flow field, while the other set of characteristics which are inclined upstream, meaning that they bring in information from infinity and hence they carry no perturbation. So, carry no perturbation this set originates at infinity and brings in perturbation to the wall. However, since there is no the perturbation is not created on the wall at the infinity. So, these are carrying no perturbation, while this originates at the wall and carries perturbation to the field. So, this is the reason that for flow over the wall only the function f is important. Hence, g is not required for flow on the upper surface of the wall. However, if we consider the flow on the lower surface, then this is what is originating at the wall and carrying the perturbation to the field, while this then is originating at infinity and carries no perturbation. So, for the lower for flow on the lower surface, G gives the solution. Now, let us see that Cp on the wall, the pressure coefficient on the wall two alpha h by beta cos alpha x, which can be written as two by beta dy dx wall. And if you remember, this is the same pressure coefficient that we obtained in case of weak wave theory or linearized shock expansion theory. So, we get the same result here also. One more thing, that this is now antiphase to the wall. Out of phase with respect to the wall. Maxima and minima are shifted by a phase of pi by 2 with respect to the maxima and minima of the wall. So, we have pressure distribution antisymmetrical to the crests and troughs of the wall. And we can show this for subsonic and remember the pressure is. So, these are of course normal direction. For the supersonic case, however, this has and this of course clearly shows that for if the wall is symmetric as you have considered, there will be no lift in both the cases. However, in this case there will be a drag force acting, while there is no drag force here. Now, the magnitude of the drag force per wavelength can be written as C d equal to 1 by L 0 to L this gives the component along the flow direction, component of the pressure coefficient along the flow direction, which is say C p sin theta is nearly equal to C p theta, which is C p dy dx, of course, this dy dx of wall. Now, as we have already seen that the C p is written as two by beta into dy dx. So, this becomes dy dx square dx. And this we can replace by a average where this average is defined So, once again we have seen that there is a drag in inviscid two dimensional supersonic flow, which is called the wave drag. Because of the wave nature of the solution of supersonic flow. Again, considering the range of validity as before, we can see since first of all we have considered the linearized supersonic flow, or that is supersonic flows which can be linearized, and this implies that the coefficient of d 2 phi d x 2 on the left hand side, the coefficient of d 2 phi d x 2 d x square on left hand side is much larger than coefficient of d 2 phi d x 2 on right hand side, or now u by u infinity maximum, as we have already seen, is alpha h by beta. which again gives and we see that we have again obtained the same relation as we have seen in case of a subsonic flow, that the linearization can be used only if this condition is satisfied, and if not, as this quantity moves towards 1, the applicable validity becomes poor, and when this reaches very close to 1, this approximation cannot be used, and this term on the right hand side cannot be neglected, meaning this suggests when the flow will become transonic. Now, if we combining with the subsonic case, combining the result with subsonic case, we have so outside this range linearization is possible. Complete linearization is applicable outside the range, and the flow is transonic within the range. And as you have mentioned earlier, or as you can see that alpha h, the parameter alpha h can be related to the maximum slope of the body. So, we can replace this alpha h by the maximum slope, and this gives a concise definition of transonic flow. So, you can see this gives us a definition of transonic flow. If theta is the slope of the body, then and this term is usually called the transonic parameter. Let us denote it by chi. So, see that whether a particular flow can be called transonic or not depends on the free stream Mach number, and particularly and 3 by 2 exponent for the factor 1 minus m infinity square, the slope of the body, and also the specific heat ratio gamma. That means, it depends on the gas itself. So, for a given body and a given free stream Mach number, the flow may not be transonic if gamma is such that this condition is not satisfied. We can also see that the small perturbation also leads to the earlier assumptions that and similar to subsonic case, small disturbance approximation if alpha h by root over m infinity square minus 1 is much less than 1 and alpha h root over m infinity square minus 1 is much less than 1. This also you can see as before using the same approach, that is u by u infinity and v by v infinity v by u infinity are much smaller than 1 to get this relation, and the higher order term in the wall boundary conditions are negligible if this is satisfied. So, hence these are the requirement for the small disturbance approximation to be valid. Now, with this we can find what is the supersonic thin airfoil theory. This will give us supersonic thin airfoil theory. Now, from the solution of our wavy wall, we have seen that disturbance propagated along downstream running Mach lines only. Disturbances propagate along downstream running Mach lines only. Hence, the solution for the solution for the upper surface phi x y equal to function of x minus beta y for y greater than 0 for lower surface Now, the specific form of f and g can only be obtained by satisfying the wall boundary condition, and so boundary condition on upper surface gives us u infinity dy dx on the upper surface is again approximated to d phi dy at y equal to 0, and which is d phi dy is minus beta f prime x or f prime x is minus u infinity by beta dy dx on the upper surface. Similarly, on the lower surface and once again this must be remembered that beta in this case is root over m infinity square minus 1. These are also the velocity component on the wall, that is u on upper wall and similarly this is u on lower wall. Hence, the pressure coefficient can be written as minus 2 by u infinity f prime x on the upper surface and minus 2 by u infinity g prime x on the lower surface. Now, substituting here f prime and g prime, this gives C p on the upper surface as 2 by and on the lower surface So, see the pressure coefficient on the airfoil surface is quite easily obtained from the solution of the wave shaped wall or using the linearized problem of course, and what we can see that this leads to a local inclination theory, that C p at any point on the surface is simply related to its slope, surface slope at that point. So, C p related to local surface slope. C p at any point on the surface of the airfoil simply depends on the slope at that point, and of course, the free stream Mach number within the framework of thin airfoil or linearized theory. So, to summarize, what we have done today is solved linearized supersonic flow past a wavy shaped wall, and the most important thing that we have observed that there is no exponential attenuation factor in case of a supersonic flow. That is, the perturbation in a supersonic flow extends to far away, theoretically to infinity, and the perturbation remain constant along the characteristics lines. Also, we have seen that the disturbances propagate along only downstream running Mach lines. Hence, for the solution over the upper half of the flow, the only function required is the function f, and similarly for the lower surface the solution that is required is the function g. Considering the validity of the linearized approximation, we have come to an explicit definition of transonic flow, and we have defined a transonic parameter, which we have seen that depends the free stream Mach number, in particular to the Prandtl-Glauert factor we raised to the exponent 3/2. It also depends on the slope of the geometry, but surprisingly it depends on the gas itself. So, whether a flow at a particular Mach number over a particular geometry is transonic or not depends also on the gas itself. Also, we have seen that as before we have found a drag force acting even in two dimensional inviscid flow over a body. So, we confirm the fact again that in supersonic flow there is a drag even if the flow is inviscid and two dimensional, the drag which we called wave drag, and in this case also we have evaluated the wave drag. Then finally, we have extended this solution of flow over a wavy wall to flow over a thin airfoil, and we have developed what is known as the supersonic thin airfoil theory, where we have seen that the pressure coefficient at any point on the airfoil surface depends only on the local slope and which also depends on the free stream Mach number. So, with this we conclude our definition that this thin airfoil theory within the framework of small perturbation theory leads us to a very useful, but very simple result for flow past an airfoil, and of course, as you can see that this solution will be also applicable to a 3-dimensional geometry, except near the tip where the effect of 3-dimensionality will come in.